simple probability today, along with what are independent events and some problems where we do them with and without replacement. All things that you've done before, but we have not yet reviewed them this semester. And we will get to some harder ones later on in the semester. So first, just a little bit of reviewing what we are talking about. When we talk about the probability of an event, that event might happen, it might not happen. We count up all of the possible things that might happen, and that tells us what goes in the denominator. In the numerator, we put how many different ways the thing that we are wanting the probability for can happen. So the things that match our probability in the numerator, all of the total possibilities in the denominator. When I am talking about independent events, I'm talking about events where what happens with the first one in no way changes the probability for the second one. Then they are independent events. When we calculate those probabilities, we do them by multiplying the individual separate properties. Many of your homework problems are going to be ones that talk about the probability of rolling dice and adding up how many you can move in that turn. So think of it as playing Monopoly. What is the probability that you get to move 12 on your next turn? Or what is the probability that you get to move 7 on your next turn? You're trying to land on boardwalk or something as you are playing that game. So we are going to fill out a little chart for easy reference. You can keep this in the front of your book so you don't have to repeat this every single homework problem or find the chart on page 500. So we are going to imagine that instead of the standard 2 white dice when you're playing Monopoly, you're playing with 1 red die and 1 blue die. So if we get a 1 on the red and a 2 on the blue, that's a different outcome than 2 on the red die and 1 on the blue die, even though they're both a 1 and a 2 and you move 3. So as far as filling out the chart, that's what's going on. So to fill it out, if you get a 1 on the first die and a 1 on the second, you get to move 2 in that turn. If you get a 1 on the first and a 2 on the second, you get to move 3 on that turn, and so on. You guys just go ahead and quickly fill this out. I know you can easily fill all of this in on your own. So how many different outcomes are represented in this table that we've just filled out? And again, a 1 on the red and a 4 on the blue is different from a 4 and a 1, and that's different from a 2, 3, which is different from a 3, 2. How many different outcomes are up there? So there's 36 up there. So for this one, we have 36 possible outcomes. So let's suppose that I wanted to talk about the probability of getting a 12. What would that be? How many 12s are in that table of outcomes? Just 1, so 1 over 36. So you'll have a 1 in 36 chance of getting to move 12. What if I asked for the probability of getting to move 10 on your next turn? How many 10s are up there? So 3 out of the 36 we would reduce to 1/12. So pretty easy review so far, as are some of these problems. So let's go through. 2 fair dice are rolled. What is the probability of getting a total of 8? So you guys told me there are how many total possible outcomes? So our denominator is going to be 36. How many 8s did you write in your table? So there were 5 different ways of getting an 8. This is the notation that we use. P of whatever it is that we're looking for, the probability of an 8, is 5 out of 36. Right? Let's do probability of getting a total less than 7. So for that one, I'm going to say probability, and then I'm going to do less than 7. and you've still got 36 outcomes. But this time, a total that is less than 7. Which numbers am I interested in on this table then? So the 6, 5, 4s, 3s, and the 2. We need to add all of those up, so count all of those up, and how many do we have? 2, 3. How many did you get? 15. So we are going to write that down, that we had 15 out of the 36. And what can we reduce those by to simplify? Or what do we divide by to simplify? Divide by 3, and we have 5 over 12. Okay, now I'm going to change it up just a little bit. What is the probability of getting a number 7, a number less than 7? So I'm still doing probability less than 7, but this time with only one die. What's that probability going to be, Colin? Can you use that table on this one? That table is only for 2 dice and the sum. When you're doing just one die, you don't use the table. How many sides are there on a die? Yeah, the numbers 1 through 6, and how many of those numbers are less than 7? So all 6 of them. So you can write that as a 1. You can write that as 100% if you prefer using percents for your probabilities. How could we change the 5/12 to a percent if we wanted that? How do you change a fraction to a percent? You guys know this. Divide it. You pull out your calculator, punch it in, change it to the decimal equivalent so that you can see what the percent is. And sometimes you will want to do that. Right, a few different kinds of problems. Okay, this time I'm going to do 2 things one after the other. This time I am going to toss a coin and then roll a die. So I want the probability of getting a heads when I toss the coin, and then a 4, so I write that the probability of H comma 4 equals. When I toss a coin, does that in any way change the probability of what happens when I roll a die? If I get heads, does that somehow change how many sides are on the die or anything weird like that? No. So these are independent events. So to get my answer, I am going to figure out, well, what's the probability of getting a heads by itself? And then the product, so I'm going to multiply this by the probability of getting a 4 when I roll the die. So everybody, what's the probability of getting heads when you flip a coin one time? 1/2. And what is the probability of getting a 4 when you roll one die? 1/6. There are 6 sides, only one of those is a 4. Multiply, and we have a 12th. Okay, what if I forget about the coin for now, and I pull out a die, and I want to know the probability of getting 4 6 times in a row. So 1, 2, 3, 4, 5, 6. When I roll the die, and I get a 4, does that change the die before I roll it the next time? It doesn't get rid of, I don't just have 5 sides now. So it stays the same, so they're independent. So what am I going to need to do to come up with this probability? Gavin? So we're going to need to take the probability of getting a 4 the first time times the probability of a 4 the second time, the third time, the fourth time, the fifth time, the sixth time. You okay if I use an exponent on that? And then punch that in on your calculators, because I don't think you've memorized 6 to the 6th. I sure haven't. And we get 1 over 46,656. What about the probability of I flip a coin and I get heads 12 times in a row, and now I want the probability of getting heads on the 13th toss? Is that what I just did? Is that probability of heads, heads, heads until I get 13 of those written out? No, why not? What's different? Okay, this does not say what is the probability of getting heads 13 times in a row. It says what is the probability of getting heads on just one toss, the 13th toss. And what will that be? Just 1/2. Many of your homework problems will simply say on the next toss. So my caution is, read carefully. What are you being asked? Questions to that point? Okay, we're going to move to some of the ones that I think are a little bit more fun personally. So we've got like marbles in a jar, and we're going to take some out, and the probability of getting this color and then that color and figuring out what is going on with those. So we want to get the probability of a blue first and then a yellow. So probability of blue first and yellow second. Don't really need those subscripts. I'm just doing that for emphasis. I need to figure out the probability of getting a blue first times the probability of getting a yellow second. So when I pick that first blue marble, how many total marbles are in the jar? Everyone. That's not everyone. And how many of those 15 are blue? I would like for you to get in the habit, write these down without reducing until you have all of the ones written down for the problem, then reduce and then do your multiplying. And I'll talk about why before we finish this slide. So that's the probability for getting a blue on the first pick. Now I am going to put that marble back in the jar. So when I pick the yellow one, how many total marbles are in the jar? We're back to 15 in there. How many of those 15 are yellow? Those are what we need to multiply. Now that they're both written down, let's reduce them. That's 1/3. This is, if I divide both of those by 5, what, 2/3? So that I come up with 2/9. Does that make sense to everybody? Okay, what if we don't put the marble back? Same probability or different? So let's figure out what happens if we don't put the marble back. We are still doing the probability of a blue, then a yellow. So when we pick the blue one, how many blue ones are there in the jar? 15. Or I'm sorry, 15 total. How many blue ones? 5. We do not put it back. So now we get ready to pick the yellow one. How many total marbles are in the jar? 14, so that denominator has changed. How many of those are yellow? Sure? Now that we've written them down, then we can reduce them. This is why I want you to get in the habit of writing them. You will make fewer mistakes with that second denominator. If you haven't reduced it yet, you'll be more likely to get 14 as the correct denominator for the second part. We reduce both of those, and we have 1/3. And we have 5/7, and if we multiply those, we have 5/21. So which one of those is more likely? How many think first? How many think second? And most of you are undecided. How are we going to decide for sure? Ryan, how do we decide for sure? We could get a common denominator, but I'm going to do it my way and not your way. I really do not want to deal with 189 for my common denominator. I am going to multiply this one by 7/7 and this one by 3/3 and use a common denominator of 63, if that's okay with you. And so let's see, what do I have? 14/63 and 15/63. So which one is more likely? The second way. How else could we have compared those and decided which was more likely? Evan. We could have converted those to the decimals. I had a student last period who also said, well, just thinking about it, even without comparing them numerically, picking the blue one, that probability doesn't change. But for the second pick, you've got a 10 out of 15 chance the first way, but 10 out of 14 the second way, and knowing that that was more likely for the second way. So at least 3 different ways of figuring that out. Before we leave this jar problem, what if we did a little bit different problem, and I still have, what was it, 5 blue and 10 yellow in the jar when I start. This time I want to get the probability of getting a blue and then getting another blue and not replacing the marble in between the picks. So Billy, what's the probability for the first blue? So 5 out of 15. And again, thank you for doing that without reducing it. We do not put it back. So now how many total marbles, everybody? 14. And since it's blue, my second denominator is 5 again? Why 4? Because we kept the blue one out, so that changed how many blue ones are in there for that second pick. And so then if we multiply that, 1/3 and 2/7, we get 2 over 21. Everybody good with that? Okay, last type of problem that we are reviewing today, pulling cards out of decks of cards. And largely, I just want to review and make sure that everybody remembers what a standard deck of cards is, because some of the problems they don't tell you. This one says, how many total cards in a deck of cards? 52. And tell me something about those cards. They're divided into suits, right? And how many suits are there? 4. What are the 4 suits? So diamonds, hearts, clubs, and spades. What colors are those? Which ones are red? And the blacks are the clubs and the spades. So what's the probability that I pick a black one? So 1/2, but if we were writing it out, we'd probably do the 26 over 52 if we then had to multiply that by something till we got all the numbers up there. How many cards are in each suit? 13, and they go 2 up through 10, Jack, Queen, King, and Ace. So everybody on track with that? All right, so for this one, we want the probability of a diamond and then a heart. So probability of a diamond is how much? So 13 diamonds out of 52, which we'll reduce later to 1/4. And then we put it back or don't put it back? We do not put it back, so we keep it. How many total cards are left? And how many of those are hearts? 13. Now we reduce this to 1/4 so that it's easy to finish up 13 over 204. Questions from anybody on this? As I said, we will do some harder probability problems a little bit later this semester.